Okay, the change of base formula for logarithmic expressions. We can use this formula basically to switch over to a logarithmic base that we can use our calculators for if we're looking for an approximation. So the typical ones are the common log or the natural log, log base 10 and ln or log base e are the ones we typically are allowed to use on our calculators. So this formula allows us to switch from whatever base we're given from the original into whatever chosen base we want, usually log base 10 or log base e, so we can use our calculators. Let me first explain where this kind of comes from though, before we just plug in and do a couple examples and get decimal approximations. So if we're starting out with log base 5 of 3, let's go ahead and set that equal to a dummy variable such as y. If we wanted to, we could use the definition of logarithm and switch this from logarithmic form over to exponential form. So that would be 5 raised to the y power equals 3. Now, in solving down this type of equation, it would be nice if we could rewrite both sides with the exact same base on both sides, like 3 to a power on both sides or 5 to a power, but that's kind of challenging on this one. So instead, what we're going to do is we can apply a logarithm of our choosing to both sides. What I mean by that is I'm going to plug both sides into a logarithmic function. I'm going to go on this one and choose the common log. So I'm going to take the common log of 5 raised to the y power equals the common log of 3. And because logarithmic functions are one-to-one, that's what allows us to apply this to both sides and this still remain equal. But the next thing that we're allowed to do is, now that we have a logarithm involved, we're allowed to use the properties of logarithmic functions. So one property that I noticed on the left-hand side is what's on the inside of this logarithm is all raised to an exponent. So what we're allowed to do next is move this exponent down in front and make this y multiplied by log of 5 equals log of 3. And from here, we've moved the y out of the exponent. It's being multiplied on the left-hand side. So the last thing we need to do to get y on one side by itself is divide, counteract that multiplication. So we're going to divide by log of 5. That'll isolate the y on one side by itself. And now we have an expression that we're allowed to put into our calculator. As you can see, we can punch in log of 3 divided by log of 5, and we get approximately 0.6826. And that's a non-terminating, non-repeating decimal in this situation. I chose the common log. If you'd use natural log at this stage instead, we would get to the exact same decimal approximation at the end. Nothing really told me I had to use common log as opposed to natural log. All right, so that's where it comes from, like kind of what generates this formula and why we're allowed to use it. Let's just rewrite these next ones and go ahead and get decimal approximations or get approximations for them. So when you have log of 1/2, log base 1/2 of 8, we could rewrite this. Let's use a common log, log of 8 divided by log of 0.5 or 1/2. And getting that put into our calculator, I believe this one turns out to be exactly -3 using my calculator. And I know these are kind of rapid fire, but just get the pattern down. It's log of whatever's on the inside divided by log of whatever the base is. So log of 10 divided by log of 2. And if you wanted to, you could simplify this down. That's base 10 of 10. Log base 10 of 10 turns out being 1. So this would be equivalent to log 1 divided by log of 2, which works out to be approximately 3.3219. And then one more of these, just get an approximation for a log base 5 of 100. Maybe we do a natural log of 100 this time over the natural log of 5. Should be noted, you can't cancel out and say 100 divided by 5 makes 20, or we can't cancel out these natural logs because their functions don't go doing anything like that. But this is going to be, I guess I should use approximately 2.86135. ... Keeps going, round appropriately. All right, so I hope this crash course and change of base formula helps out if we ever need to get decimal approximations for logarithmic functions that don't have nice bases from the very beginning. It is a handy formula to use. In the future, we'll be using the steps that I went through initially on this video to help solve down some of these logarithmic equations. Hope this helps. Good luck.